I have fun though. That's all that matters. They're like, oh, that dude's gonna fall again. So, anyway, equation of a sphere is defined based on the radius of whatever the sphere is, or what the dimensions of the sphere are. So it works the same way as a circle. Right? The circle in general is Pythagorean in nature. It's just infinitely many right triangles going around. Right? So it's the same idea as a sphere. It's just really omnidirectional. It's going everywhere. So what we want to do here, if we're going to write this standard equation of a sphere, which has a very circular feel to it, it's going to be essentially to find the radius, because once you find the center, if you know the radius, then you know the equation of the sphere. Right? So our first challenge would be, I suppose, to find the midpoint. Oh, it's at the center. Sorry, I'm thinking of the wrong problem. They gave us the center. So we're already good there. Oh, that is not my marker. So we just need to find the length of the radius, so the distance, again, the difference between corresponding values squared. Right, so 11 squared, 121, plus 10 squared, 4 squared, 16, and 6 squared, 36. 52. Is that root 173? Yeah? Ugh. All right, well, it's going to get squared anyway. Oh, the difference between the x values, 10 minus negative 1.
Oh, okay.
Shockingly, I didn't screw that part up, but I almost screwed up the 7 minus 3, which is obviously not equal to 10, but somehow I wanted to make it equal to 10. All right, so this is our radius. We have the center again, so it's x minus whatever the x value of the center would be, so x minus 10 squared plus y minus 7 squared plus z minus 4 squared would be equal to 173. All right, so not something that you could verify on your calculator, but something you could verify on Geogebra. You could, I think, do it on Desmos also, although I have trouble with three-dimensional stuff on Desmos. It's, for me, easier to do it on Geogebra, and that's only because there's a dedicated app it's specifically designed for 3 dimensions. So at least in the early goings, you may want to consider just checking your work on Geogebra. You know, it doesn't have to be on a computer, because the website on your phone works pretty well, or at least it works as well as the computer. I mean, sometimes, I got like fat fingers, so sometimes it's a little iffy, but you know, you can kind of make your way around it. So x minus 10 squared plus y minus 7 squared plus z minus 4 squared equals $1.73. Big blur. Not really though, because we just zoom out some.
The 3D graph thing, that's only online, right? That's not on the app.
It's not on the app, so you have to go to the website. Let's get rid of the plane. I don't need that. It's bothering me. My axes, I thought they would be here, but they don't seem to be showing up. But we can live with that also.
And you need the plane as well. You're gonna need the plane.
Well, I'm gonna show a different way of verifying it. I just want to change some settings though, because sometimes the colors are a little too dark. I like this one. This shows up pretty nice, like maybe even that one. you know, it's a little brighter. So they gave us a point, -1, 3, -2. And as long as it shows up on the surface of the sphere, I'm pretty satisfied that it didn't just screw this whole thing up. So, and it does. And you can plot the center too, but I'm pretty confident that it didn't botch it. So, but you know, just for the sake of consistency, that looks like the center, and that looks like it's on the surface. All right, so. The other thing I like about GeoGebra is if you know some math words, so does it. So just start typing the math word that you know, and odds are there's a function related to it. So I wanted to draw a line segment. I could have drawn a line, but also, you know, the emphasis on vocabulary for a math teacher is probably a little bit more than maybe a student would emphasize. So you might say line, where I say segment. Right? So I automatically think segment. Line is infinite, it goes forever. If I only wanted to connect 2 points, I would want just a segment. Right? That looks like a radius. That looks like a segment connecting a point on the surface and the radius of the circle itself. And of course I can make it like rotate and stuff. Yeah, it was just too close in, I guess. You know, just kind of get it moving. I mean, that doesn't do anything in terms of giving us a better answer. It just makes it look cool. So.
Screensaver.
Yeah, exactly. What is it? Screencast-O-Matic? I think that's what it's called. It's like a cheap version. Like it's a free version anyway. That it'll allow you to record your screen in like short bursts. So I'm sure you probably know the better versions of that. Anyway, number 2 is basically the same idea. That's what I was alluding to in the previous question where I said, oh, let's find the midpoint. But in this case, we didn't know the center. If we know that these are 2 points on the circumference of the sphere, so on the outer surface of the sphere, specifically forming the diameter of the sphere, it's important that we know that it does go through the center, because if it was some other line segment connecting 2 points on the surface of the sphere, then there's no guarantee that the midpoint of that would give you the center of the sphere. It would give you the center of a sphere, just not the one you're looking for. But in this case, you could find the midpoint and then find the distance from that midpoint to one of the 2 points, P or Q, and that'll give you the length of the radius, and then you can go from there. Okay, so I'll pop a little star on that bad boy, now that I flat out told you how to do it. And it's at the 8:15 mark in this video, if you're wondering later on how to do it. I know we went over it in class. But that would, of course, require you to write down that it was at the 8:15 mark. All right, vectors in space. I used to have much more elaborate notes related to this topic because I thought it was necessary. Then I taught the course a few times, and I realized it's probably completely unnecessary because all we're doing is rehashing everything in 2 space, just adding a 3rd dimension to it.
You mentioned at one point when we were talking about the distance formula. You want us to do proofs during the test. Like, what would you want us to do? Like exactly what you showed before, how you develop the equation?
Yes. So, if you want a very good sense of what would be expected of you, this is the part where it seamlessly transitions from screen to screen, and I don't have to wait.
No signal.
There it is.
No signal. Are you recording this?
I am, yeah. The extra practice review section on my website, if you go to the review problem set, well, this is the answer key of it, but whoops, there was a problem loading more pages because the internet here sucks. Asgard. Yeah, because that just brings you to another page. All right, well, you'll just have to take my word for it. If you scroll down, like all the way to the end, you'll see all of the different possibilities of things I could ask you to prove. And then from those oh, here we go. Just a little refresh action. Yeah, we're getting there, getting there, getting there. Possible proofs, derivations. So any of these are possible. I'm only going to choose one to put on the test. All right, so if you know them all, you're good. People have rolled the dice in the past and only known like 2 or 3 of them and just hoped that it was going to be one of those 2 or 3 of them. And sometimes works, sometimes doesn't.
When are we gonna start the material?
The end of class on Tuesday.
Like, is it gonna be another 3 pages, 4 pages?
A bunch more pages. Yeah, yeah, we got a little ways to go. So all of this stuff is consistent from vectors in 2 space. So vectors in 3 space, vectors in 10 space, it all works the same way. All right, so it's just, it would be rehashing the old stuff. Even unit vectors, except you have a 3rd component as opposed to 2 components. All right, so it's easy enough. So we have coordinate P and Q, and line segment PQ forms the diameter of a sphere, and we want to find the equation of this sphere. All right, so big key ingredient there, I mentioned it last time, was the idea that it forms the diameter, which would mean that its midpoint would be the center of the sphere. So that's what I'm going to do, is find the midpoint of PQ. And so that's just the average of the 2 coordinates. All right, so -5 plus 3 is -2, divided by 2 is -1. 2 plus 4 is 6, divided by 2 is 3. 3 plus -1 is 2, divided by 2 is 1. All right, so this would be the center. All right, so then what I need is the distance between the center and one of those 2 points, or I could find the distance between those 2 points themselves because they represent the diameter and just chop that in half. You got a lot of possibilities. All right, so if you want to avoid compounding an error, aka, I'm not confident that I did this right. Maybe I made a mistake here. So if that's the case, then working off of this would create a new mistake. Right? If that's the case, then maybe you want to find the distance between P and Q. And then, like I said, chop that in half. Right? So the difference between these 2 values, the corresponding values, -5 minus 3 is -8. And then we square that, so 64 plus 2 minus 4 is -2 squared is 4. 3 minus -1 is 4, squared is 16. All right, so we're looking at, looks like 84, square root of 84. All right. And so if I want, and that would represent, again, the distance, but it's specifically the diameter. All right, so the radius would be equal to 1/2 of that. All right, so then I would pop that into my equation. X plus 1 squared plus y minus 3 squared plus z minus 1 squared is going to be equal to the radius squared. All right, so I have to square that number, which is going to be 84 over 4. So that's going to be 21. All right, and so this would be the equation of the sphere. All right, and so in theory, if you pop this into Geogebra, you should be able to see that these 2 points would fall on the circumference or the surface of this sphere. And if you were to draw a line segment from them, it should at least appear to go through the center, which would be at -131.
How did you find the center?
Just the midpoint formula. So it's the average of corresponding x, y, and z values. It's the same idea as if you were to find the midpoint in 2 dimensions, except you're just doing it for the z value also.
How come, for example, when you're solving for the diameter, your x squared is 8 squared, but you're not adding 4? I don't know. Like, how did the center translate into the diameter?
Oh, the center just actually gave me the HK and, well, actually that wouldn't be H and K. It'd be X1, Y1, and Z1 values for the equation of the sphere. If I wanted to, I could find the distance between either one of these 2 points and the center, and that would directly give me the radius. But I opted to ignore that and just find the distance between these 2 points in hopes of avoiding compounding a mistake. Right? If I screwed this up, so I'm just thinking, I'm in like test-taking mode. If I screwed this up, I'd lose credit for making that mistake there. But if I also screwed up the radius, I'd lose credit for that too. Right? So if I go back to the original coordinates, I'm less likely to make a mistake, assuming I know how to find the distance between 2 points, because I'm not working off of something that's incorrect itself, right, in and of itself. All right, Christian.
We didn't derive the equation of a sphere at all, right?
No.
Okay, like before.
No, we didn't.
When having an x value minus our center value, what x value do we use? The p values or the q values? Would we use the
You're using the center.
for x minus 1 squared?
For x?
Oh, sorry, z minus 1 squared.
It's coming from this.
Yeah, okay.
And that was the reason why we found the midpoint to begin with. So the dot product, the plot thickens. So we're going to learn about the dot product, and next class we'll do cross product, and that's where the unit will end. But and so little applications of the cross product. There's also calculator shortcuts for some of this stuff. Sometimes it's not really as worth it as you might think. You know, some other topics it's like, oh, thank God we have these calculator shortcuts. And then other topics it's like, I think maybe the calculator shortcut takes more work than doing it out by hand. So yeah, well, it's risk reward, I guess. But anyway, the dot product is really just the sum of the product of the corresponding components from 2 vectors. All right, and we'll get into what it all means as we go forward, but for now it's just a skill. All right, so if I want the dot product of u and v, I'm going to take the corresponding parts, multiply them, and then add the results. So we're looking at -3 plus 15 plus 0. So the dot product is equal to 12. All right. Again, what is the dot product? We're getting there. Learn the skill first, then we talk about why it's useful. Concept of orthogonality, we'll get to that, but this is going to lead into that concept. If you have any idea what orthogonal means, this is going to support that idea. Anyway, the scalar product, if we're talking about a scalar product between 2 vectors, then we're talking about a dot product. All right, so scalar product involving 2 vectors, or if they say a vector scalar product, then you're talking about a dot product. All right, they mean the same thing, it's just the verbiage is slightly different. All right, the IJK notation, it just takes the place of the vector notation. And so if you want, just for consistency, you might consider writing P as 10, negative 4, 7, and Q as negative 2, 1, 6. In order to find our dot product, P dot Q, which would be, again, the sum of the product. So negative 20 plus negative 4 plus 42. So is that 18?
Yeah.
So another meaningless number at this point. Again, skills now, context, underlying meaning. That comes later. All right, some properties of the dot product. All right, so anytime you throw some properties at some concept, it adds a little bit more meaning to it, because, like, okay, we have a skill here, but if there are some known properties and theorems associated with those skills, that's good news, because that kind of, it supports the idea of the importance of the concept itself. All right, so at minimum, we could use the commutative property, associative distributive properties, in conjunction with the dot product, which is great. But again, what are we using it for? We'll see. The property of magnitude is a big one. We'll see that in action in a couple of minutes. But below, you can see that there are just a couple of applications of these properties. All right, so I'll put some stars on these so that you can try them on your own, because it's really just a question of dot product in particular order. All right, so what am I doing here? I'm finding the dot product of A and B first, and then multiplying the results by C. All right, so here I'm finding the scalar product of an actual scalar and vector C first, and then taking that and multiplying it by A using the dot product. And then the third one, or number 5 in this case, is the magnitude of B squared, but the property of magnitude tells us that that's equivalent of the dot product, equivalent to the dot product of B in itself. All right, so it makes it a little bit simpler than actually finding the magnitude of B and then squaring it. In fact, let's take a minute right now and talk about this one, because as I flashed through the review for the test, you might have seen that this is one of the possible proofs. All right, and you can see this is actually a nice one. It's not bad at all. All right, but it's in general terms. If we're working in 3 space, then I would establish V, vector V, as some unknown, completely unknown vector. All right, so I got to come up with some variables that represent the components. I'm going to keep it simple, relatively simple, and call it V1, V2, V3. Try to stay away from subscripts, but in this case it seems to make sense. It's vector V, first dimension, second dimension, third dimension. Right. You could do that too, either way. So in this case, if I want to find the product of V in itself, the dot product, I would be taking V1 and squaring it, adding to that V2 squared, and then adding to that V3 squared. All right, so that is the squared value of each component. But really, I mean, could I just square it? Well, I multiplied it by itself because it's the dot product of V and V. So V1 multiplied by itself, V2 multiplied by itself, and V3 multiplied by itself. That's pretty close to the magnitude formula. It's just it's missing a radical. All right, so let me introduce a radical. No, it's all good. No, it's not. Because I can't just introduce a radical. Unless I do what? Square it, right? a radical squared doesn't change the value of whatever it is you started with. Like the square, if I start off with a 2, slap a radical on it, it becomes radical 2, square that, it goes back to being a 2. So it's equivalent. All right, so that's the same thing. But the thing that's contained in the parentheses, that's the definition of the magnitude of V squared. So inside is the magnitude of V, and we still have that leftover power of 2. So the dot product of V in itself is equal to the magnitude of V squared. All right, so that makes this an interchangeable operation. So it's all a matter of convenience. If I find it easier to figure out what the dot product is, then I can use that to figure out what the magnitude squared is. Right? If I just need the magnitude, right, so I find the dot product and then take the square root of the result. I no longer have to actually find components, use the Pythagorean relationship and things like that. Right? Especially, I mean, in a sense, you're doing that anyway. But if I already have to find the dot product for some other reason, then I can use that information to go a little bit further with it. Right? So it's a pretty cool realization, I think. I guess their properties, which makes some relationships a little overkill, I guess. Redundant is the word I was looking for. All right, so we're just applying the properties here. And you see how I just, off on the side there, proved, and this happened last class, the property of magnitude. But any of these other properties, you'd play it out the same way. All right, so if I needed to prove the commutative property, I would just come up with vector u and v in general terms. So instead of v1, v2, v3, if I'm looking at vector u, it'd be u1, u2, u3.
Somebody at some point mentioned that you can do vector multiplication with the solve button. Is that true?
I don't know about the solve button, but you can do it with just the squiggly brackets. I could show you real quick. It's something. All right, anyway, so these examples are all property related. We have, again, the commutative property, which is pretty, I don't want to say universal, but it's pretty commonplace. Now, odds are, if you're working with an operation, odds are it satisfies the commutative property, except for when we get to cross product, except for the cross product. All right? It tells us that if you reverse the order, the result is the same in the case of the dot product. Associative property is telling us that if we reorganize, we get the same result. So if it's C dotted against, C multiplied against U dot V, where C is some scalar, then you can take the C and multiply it by the U. And so we're reorganizing it so that the C is grouped with the U, and take the result and dot it against the V. Or we could group it with the V. All right? Distributive property, it works pretty much how you would expect a distributive property to work, except we're utilizing the dot product. So we're dotting the U against the V and the U against the W, and then getting the sum of the results. All right. So in the case of number 3, it's pretty clear what we should do first, unless you want to make use of the associative property, which would allow you to reorganize this. Why would you reorganize it? Well, if it's more convenient to dot B and C against each other first, and then take the result. Let's say, for example, if you know that dotting B and C together will give you the 0 vector, then start with that, because every calculation that's based off of that is going to be much easier to handle. All right, so in this case, it doesn't really make a difference, though. All right, so I'll tackle the A dot B first. All right, so we're getting the results. I'm going to sip of water. So 0 plus 4 plus negative 12, so minus 12. It's going to be negative 8. All right, so that's going to be negative 8C. All right, and that's the calculation that I showed you on the calculator a couple of minutes ago. I mean, we all have our own strengths and weaknesses. One of my strengths happens to be simple addition and subtraction. I'm pretty good at that. Also pretty good at simple multiplication and division and simple like powers and stuff. Right? Emphasis on the simple. You know, you throw some funky numbers in there, I got to pause and maybe reach for a calculator like the rest of humanity. But I'll tell you that it felt like I did this quicker by hand or / in my head than doing it on the calculator. Just finding the squiggly bracket took me longer than doing this problem. All right, so and I got the same answer, -8. You know, that hopefully is the proof that you might be looking for, right? Or at least evidence. So this is a scalar multiple, -8 times c, right? So I'm just multiplying each component by a -8. So we're looking at -40, +8, -24. All right, in number 4, we're dotting A against 2C. So I'm going to rewrite A. 1, 2, -3. I'm dotting that against 2C, so double C. 10, -2, 6. So we're looking at 10 plus -4 plus -18. And so 6 minus 18 is going to be -12. All right, and the last one is the one that is addressed by the property of magnitude. It's one of those questions that you can go either way with. You're comfortable at some point, hopefully prior to tonight, with the idea of finding the magnitude of a vector. All right. So if that's the case, then you could find the magnitude and just square the result. Or if you know the property, we know that it's equivalent to dotting the vector against itself. So this is B dotted against B. So 0 plus 4 plus 16 will give me 20. All right, so that's a nice problem if you know the property of magnitude. Otherwise, it's going to take a couple more seconds to do. All right, not impossible, not even difficult, just more time. And time is a premium, or at a premium. So I'm in the mood to invent formulas, so let's invent some more. Dot product of two vectors is the product of magnitude of each vector and the cosine of the angle between them. All right, so this looks like it comes out of nowhere. I'm sure it was explained to me back in the day. But essentially or eventually it became, all right, just memorize this and use it, I guess it'll be fine. But it's actually pretty cool. All right, so what we have here is a triangular relationship. It's the difference between two vectors. And we learned 2 classes ago, I think, that the difference between two vectors is really just the sum of two vectors where one of them is negative. All right, so if I have vector u and vector v, if I want to find v minus u, that would be the same as, let me just bring it in, negative u plus v. So I would just need the vector negative u, which would be the same vector as u, just going in the opposite direction. So freehand drawing. All right, an attempt at a freehand drawing anyway. Oh no? Typo bonus. That's for somebody. In that case, it would be shift diagram. What do you think? An inch? An inch to the right? Or what would that be? 2.54 centimeters for those of you who are not inch people. Right. So that would be my negative u. And so if I want to find the resultant, I would create a parallel to v. So again, freehand drawing. make a nice parallelogram out of that. That's a nice looking parallelogram, I'll tell you that right now. And so this would be negative u plus v. And so all we're really doing is picking up that negative u plus v and putting it up over here because it would be congruent. Opposite sides in a parallelogram are congruent. We didn't have to go around the room for that one though. And so that closes the triangle. So now we have a triangle, which is wonderful. Why do we need a triangle for this? Well, if you have a triangle and that triangle has 3 known sides and an angle, you might choose to use the law of cosines. So c squared equals a squared plus b squared minus 2ab cosine c, or the other 2 possible variations. The key ingredient is that side c is opposite angle c. What's angle c? Well, it's the one that you know. All right. So the side that's opposite of angle theta, I'm going to go purple for that, is v minus u. All right. Now, v minus u is not a side. That's a vector. The magnitude of that is your side. So the magnitude of v minus u squared would be equal to, now a and b are interchangeable, so it doesn't matter. U then v or v then u. But they're still magnitudes. Magnitude of v minus u squared equals magnitude of u squared plus magnitude of v squared minus 2 times magnitude of u times the magnitude of v times cosine of theta. All right. These would all be scalar quantities, so it would be the ordinary definition of times, multiplication. However, we do have a relationship, the magnitude property from the previous page, that tells us that if you square a magnitude, the result is the dot product between the 2 corresponding vectors, all right? So, or the vector in itself. So in this case, on the left-hand side, I could say v minus, well, it would be parentheses because the whole thing, each part is a vector. We'll worry about the right-hand side in a minute, but the left-hand side is just distributive property. All right, so we would be taking the dot product between v and v. This is where notation becomes important. I mean, it's always important, but extra important, because v squared without a magnitude associated with it doesn't have meaning, because v is a vector. You can't square a vector. A vector is a directional ray. Really, what does v represent? Something, comma, something, comma, something else. All right, what are you squaring? The first part, the second part, all of it? What you can square is a magnitude. So in this context, when I'm multiplying, when I'm finding the dot product, it is the dot product between corresponding parts. But what we do with those dot products is what's going to define everything. So the outers would be negative u dot v, and we'll have 2 of those. So negative 2 dot u dot v then plus u dot u. All right. So going back to the magnitude property, if I have the dot product between 2 identical vectors, that's equal to the magnitude squared. So I'm still working on the left-hand side. Right-hand side, I'm leaving alone for now. So this is the magnitude of v squared minus 2 dot u dot v plus the magnitude of u squared. The right-hand side we could bring back into play. And then beautiful magic will happen. We have a common magnitude of v squared. We have a common magnitude of u squared. So left-hand side contains only negative 2 dot u dot v. Right-hand side, negative 2 magnitude u. Crappy handwriting, sorry. I mean, blanket apology for crappy handwriting, that's always the case, but extra crappy in this one instance. Common factor of negative 2 that can cancel. And there it is. U dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. Consequence of that new rule, that beautiful new rule, is that now I have something that includes an angle. That angle is the angle between vectors u and v. So I now have a technique that would allow me to solve for the angle that separates two vectors. I could even solve this equation for cosine theta. Cosine of theta would be equal to the dot product of u and v over the magnitudes multiplied. Right. So at a minimum, you have a formula. You can plug and chug the formula, but if you know where the formula comes from, it's something you never really have to study. Yeah. So for a question like number 6, it says find the angle between each pair of vectors. It's up to you. If you like IJK notation or the vector notation, the component form vector notation, either way is fine. I mean, they're both, they have the same parts, so what does it matter? You don't need to convert from one to the other in order to use these formulas. You just have to know the coefficients. So in the first problem, we'd be looking at cosine theta is equal to the dot product between these two vectors. So the first one would be what we'll call a vector u in our minds, I guess, and the other one would be vector v. So multiply and add on the fly. 1 times 2 is 2. 1 times negative 1 is negative 1. 1 times negative 3 is negative 3. Poor quality line. Fixing that immediately. Then we could sum that out in a sec, but the bottom would be the magnitudes of each. So the sum of the squared values under a radical. So we're going to have 2 of those. 1 squared plus 1 squared plus 1 squared is 3. So the square root of 3. 2 squared is 4. 1 squared is 1 plus 4 is 5. And then 9 squared. So 9 plus a 5 is 14. So on the top, we're talking negative 2.
Wait, why is it negative? Why is it
4 plus 1 plus 9.
squares?
So negative 2 on top, and then what is that, root 42 on the bottom? So to figure out my angle theta, theta would be equal to the inverse cosine of negative 2 over the root of 42. Degree form is fine. There's not necessarily a requirement of radian versus degrees for this particular topic. Like for polars and things like that, that there would be an expectation that you go both ways, or be prepared to go both ways. But for this stuff, I think the focus is on getting a sense of the spatial aspects of it, and to kind of have to translate everything to radians, from radians to degrees into your own mind, or vice versa, is a little iffy. So about 108 degrees roughly. So we now know that there's roughly 108 degrees separating vector u and v. All right, so we now have a technique that allows us to find the angle between the two vectors. All right, so the second problem here, number 7, is along those same lines. But it brings us to a concept called orthogonal vectors, which talks about the idea that the dot product is equal to 0. If the dot product between two vectors is equal to 0, then we call whatever those vectors are, whatever they're defining, the relationship to each other would be orthogonal. So then if we go back to our cosine formula, let's just kind of play this out for a second. If the dot product of u and v was equal to 0, what would the entire right-hand side of this equation be equivalent to? 0. What angle in the unit circle has cosine equal to 0? 90 and 270. But let's look at the 90, for example. 90 degrees separating two vectors would make them right angles to one another, right? Mm-hmm. All right. So in space, if any two vectors are right angles with one another, I don't know why I'm using a mouse. I need to use a finger. Then they're considered to be orthogonal. So we would say form a 90-degree angle. So it forms a 90-degree angle. The issue is, in two space, 90 degrees are very easy to identify. I mean, or at least something that's near 90 degrees. Maybe it's 89, maybe it's 87 degrees, 93 degrees. But when something looks like a right angle, it looks like a right angle. It's pretty obvious. In 3 space, it's a matter of orientation, because you could have two vectors that are pointing directly at you. If that's the case, if you're looking at them straight on, how do you know that these two vectors are going to form a 90-degree angle with one another? Right? You're probably not even going to be able to see this one if you're looking at it at the wrong angle, because all it's going to appear is as a point. And if you look at it like this, you're looking at one vector that might overlap with the other. Right? So there's no way to tell from this perspective that they're orthogonal. It isn't until you turn them that you can see whether they are or they aren't. Right? So then how do you figure it out? Well, you figure it out by determining the dot product. And fun fact, it's really easy, because the dot product is just multiplying components and adding them. So this goes right back to the skill on the previous page. 10 plus 0 plus negative 10, you get a result of 0. Therefore, they're orthogonal. Fun fact, the symbol for perpendicular in 2 space is also the symbol for orthogonal in 3 space. All right. So if you didn't know that, this means orthogonal. Also, fun fact, perpendicular is a special type of orthogonality. Okay, so when you were learning about perpendicular lines, you were actually learning about orthogonal lines in 2 space. The perpendicular case is the 2-dimensional case of orthogonality. All right, so a little bit of trivia there for you. Any space, as long as they form a right angle with one another. All right, so it was formula based. I mean, we derived the formula, so we know where it came from, which is good. It was all based on the law of cosines. Do the law of cosines once to create the formula so that you don't have to do the law of cosines every single time. All right, can you imagine having to draw out the diagram, figuring out all of this information, all of this stuff here, just with the real vectors plugged in? It would be fun. Let's just put it that way. All right, so it's the dot product of the two vectors over the magnitude of each of them. All right, so at some point along the way here, the work has to get done. It's just a question of how you want to do it. So cosine of theta is what I'm looking for, at least initially. The dot product of the two vectors. So 2 times negative 2 is negative 4, plus negative 20, plus 24, over, I'll just write it in notation form. Because I'm not even going to bother figuring it out as it turned out. Because we're looking at cosine of theta is equal to 0. All right, and so we get theta equal to the inverse cosine of 0, which is going to give us 90 degrees. And that was part of the justification behind the orthogonal relationship. If the dot product between two vectors is equal to 0, then you know that it's orthogonal, right? And that's coming from this formula, because you're going to get cosine equal to 0 and cosine is equal to 0 when theta is equal to 90 or 270. So why wouldn't it be 270? Well, you can look at it a couple of different ways. Generally, when we're defining the angle between two vectors, we're looking for the shortest angle between two vectors. Right? Because if I'm looking at, I'm just going to draw two angles in space, or two vectors in space, one this way, and let's say one this way. If I wanted to go from one vector to the other, depending on which is which, I might go this way, or I might go that way. All right, so yes, theta being 90 or 270 would give us a cosine equal to 0, but it's really just describing the same relationship. Right? It's just one's going one way, the other's going the other way. Right? So it's a question of, it's a brevity. Yeah, so if you want the shortest angular rotation that'll get you from one vector to the other, then you would go with the 90. Now, direction would be important, right? So you start getting into what these vectors actually look like. That would determine whether you go with a positive 90 or a negative 90. But it's still, as an absolute measure, 90 degrees gets it done, whether you're going clockwise or counterclockwise.
Define the vectors on the bottom for U and V. How would we do that again?
Oh, it's the magnitude formula, which is the square root of the squared values of each of these added together.
Okay.
And so it's basically distance formula, just with its own vector.
Thank you.
No problem. All right, so that's that page. All right, so 8, 9, and 10 are along the same lines. So V and I, V and J, V and K. Just to touch on it for a sec here, vector V is given. I is the vector 1, 0, 0. Now we're in 3 space, so it's 1, 0, 0. If we're in 2 space, it's 1, 0. You know, so it all is relative. J is 0, 1, 0. This is all typed out for you a couple pages ago, but sometimes you need to hear it be said. 0, 0, 1. Sector 0, 0, 1.
Is I or I hat?
You can go either way. The proper way to do it is with a hat, but I'm not drawing little hats every single time.
Plus you wrote it in bold.
And I wrote it in bold, exactly. Exactly. All right, so the last thing that we're going to talk about tonight is projections and components. All right, so what you can do is project one vector upon another, or find a component of one vector acting in the direction of another. This was along the lines of that, I think it was Tabitha's blimp from earlier, where the wind was supporting her movement. And it's a question of, well, it's not entirely supporting her movement, it's in part supporting her movement. You know, so if you had, well, I mean, that's really what it is. I mean, I could go with a current in the water, but wind in the air is the same idea. I mean, if it's not blowing against you in any way, shape, or form, then it's probably supporting you. So if the flow is in your direction in any capacity, so even if it's like 1 degree in your direction, it's still going to support your movement. It's not acting against you. It may not be supporting you very much, but there is some support there. So what we want to do is we want to figure out how much of a support from one vector would impact another. All right, so that's where the projection component stuff comes into play. All right, so vector projection on V onto U is vector labeled. Of course, we have to come up with this funky notation here, proj, vector projection. We couldn't come up with anything better than that. I scoured textbooks. I've looked at, I've asked. I've gone through every source of media that I could find, and yeah, everybody uses proj and comp for projection and component. It's like, couldn't just create a symbol for it? I mean, you use hats and bars and things like that for everything else. I mean, you just seem to make it up on the fly. Use Greek letters for things when they don't need to be used, but for some reason we got to go with proj. All right, so this is the vector projection of V onto U. All right, so it is the same initial point as U and V, and the same direction as U. Represents the component of V that acts in a direction of U. I mean, there's a lot of words here, but I'll get into the specifics of it in a minute. All right, if theta is the angle between them, that's the important piece. By properties of triangles, so this is like by saying, by an entire course of geometry, we know that this is a true sentence. Right? Well, yeah, well, maybe some of us do, I guess. But do we really? I don't know. We'll find out in a minute. When expressing cosine in terms of a dot product, this becomes all of this stuff. But this, I wouldn't let it slide if I were you. Like, yeah, oh, by math magic, we have this relationship. You're like, okay, cool. Yeah, all right, magic wand, awesome. That's a great explanation. All right, so let's get into the diagram here. We have some angle theta. We have a vector V that has a magnitude. We don't know what that magnitude is, but it's there. We also have a right triangle. Now, this didn't come standard equipped with a right triangle. I dropped an altitude to make it a right triangle, right? Because what I'm looking for is the impact that V is having on U. So think of V as the wind and U as Tabitha's blimp, all right? So V is supporting the blimp in some capacity, we just don't know how much. So what we want to do is figure out, okay, if I took the component of V that's acting in the direction of U, what would that look like? And so that would end up being some distance, because vector distance represents its magnitude. I don't know how long it is, so I just ballparked it, and then drop an altitude, creating a right triangle. But that gives us the opportunity to use right triangle relationships. All right, so for example, I know the adjacent side of a triangle and the hypotenuse, so I can say the cosine of theta is equal to the adjacent over the hypotenuse. All right, so if you compare this to that, we're kind of there. So one thing to consider again is that if I call something a vector, you can't perform an operation on it. I can't just like square it or do something along those lines. Right? It's only the magnitude that I can work with. So if I know the magnitude of this projection, then I can actually divide it by the magnitude of vector v, and that would give me the cosine of theta. But more importantly, it tells us through cross multiplication that the magnitude of the projection would be equal to the magnitude of v multiplied by the cosine of theta. So the magnitude of v onto u, all right, so the thing to keep in mind is, again, v has some component that's acting in the direction of u. That is the projection. The notation's a little weird, but if you're always thinking about the subscript as being the vector that you're acting on, then that's probably the way to go. All right, so it's kind of like the notation is on the u, like it's not quite a denominator, but it's below everything else. People have said that this has helped them in the past to remember, and it's like the notation has it on the u, so we're actually projecting on the u, right? So the u is the subscript that's below everything else. So if you don't like it, I'm sure you'll figure out something else, but that's what I got in terms of mnemonic devices. So what we define, the component of v acting in the direction of u is the magnitude of the projection, right? So the projection is the vector quantity, right? So it's got components, right? It's got an x value, y value, z value, and it's going off into space. The magnitude of that is known as the component, all right? So that relationship corresponds with all this stuff. So how did I get to this? Well, we do have a relationship involving the cosine of theta. We just figured that out.
I know that.
Yeah, cosine of theta is this. So clean it up, magnitudes of v will cancel out, and so you get a nice little shortcut rule to help us figure out the magnitude of the projection, which is the same as the component, dot product over the magnitude of u. All right, nice and easy in terms of the calculation. Derivation, a little bit out there, but in terms of once you have this formula, performing a calculation, not too bad, all right? And again, I mean, not that you need me to explain this too much, but why do I ask you to derive some things on a test? Why do I give you a problem to derive? Well, if I don't, then this becomes an exercise in you reading a formula off your note card, plugging numbers in and getting answers. I don't know that you truly know the stuff that way. I don't know if you truly know the stuff by deriving formulas either, but I'm more inclined to believe that you have a better sense of the underlying concepts by deriving the formulas than just by rote calculation. All right? It's a personal philosophy. Not everybody agrees with it, but it's me. So u dot v over u, if you're looking for the magnitude of the projection. All right? A three-dimensional, or at least from a three-dimensional viewpoint, 3, negative 5, and 1. So quick sketch. So here's 3. 1, 2, 3, 4, 5. 3, negative 5, because it's x, y, z. Make a parallelogram out of that. So, and then shoot up the equivalent of 1 unit. All right, so this point here, just floating off in space, would be vector, or the endpoint of vector v. All right, now that's the same vector that we're going to use for each of these calculations, so it shouldn't be too bad. Now, vector I, right, that's the unit vector. Just do, that's this little guy right here. All right, so it's even, based on the scale that I use, it's very hard to see. It's just this little bit of sliver there. All right, so if I'm looking for that angle there, it's not as simple as, you know, two-dimensional stuff, because this one, it's not living on the XY plane. It's kind of floating up a little bit. Not too much. It's only 1 unit above the plane at its endpoint, but it's still above the plane. All right, but fortunately we have this formula that we can use to figure out the angle between the two vectors. All right, so it's the dot product over the magnitudes. So what I would do here, just off on the side, is find the magnitude of V, because that's going to come into play for each of them. So 9 plus 25 plus 1 is going to be the root of 35. All right, we just rely on that for every question. All right. So if I'm looking for the cosine of theta, it's going to be V dot I over the magnitudes multiplied. All right. You could just jump right into the calculations. I just wanted to, at least for one instance, write it using vectors other than vector u and v, you know, see what it looks like in an alternate form. So the dot product between vector v and vector I, all right, so multiply the corresponding parts and add it together, it's just going to be a 3. All right, so 3 over square root of 35 times 1. All right, it's a unit vector. There's a reason why it's called that. All right, anything that's a unit vector, whether it's an axis-related unit vector or a vector in space, it's called a unit vector because its magnitude is equal to 1. All right, so we're looking at 3 over the square root of 35. So that's just straight calculator work. I'll just do inverse cosine. I'll just jump right to it. Let me get rid of this. Theta equals inverse cosine of 3 over the root of 35. So we're not expecting something clean. And you could go radian or degree. For this topic, people like to go degree just because it gives them an answer that feels more relatable. So inverse cosine of 3 over the square root of 35 is going to be approximately 60 degrees. So 59.53. So I'll say about 59.5 degrees. Okay, so 59.5 degrees is really what we're looking at. I didn't want to round it too much to 60 degrees because then it makes it seem like it's a unit circle ratio and nobody's looking at 3 over the square root of 35 and thinking, oh, that's a unit circle ratio. You know? So that's my thought process there. J and K, both unit vectors. So I could plot them both on the same graph. This is where J would be, and this is where K would be. Oh, that's not shaping up to be much of a K. All right, so.
No, Professor, real quick, where did we get the I, J, K coordinates from?
Oh, those are just facts. So they should be a couple of pages earlier in the packet. All right, so basically just doing the same thing two more times, really. So it's more for practice than anything else. So cosine of theta, oh, that's a little thick. Cosine of theta is going to be the dot product of V and J So the x and z terms are going to zero out, but the -5 is going to still stay on board. Vector v still has the same magnitude of 35, root 35. Vector j is a unit vector, so magnitude of 1. So once you get a feel for this, you realize that there are some steps that can be skipped. But only because we're dealing with the standard unit vectors. About 147.7. So then cosine of theta is going to be equal to 1 over the root of 35 times 1. So yeah, it's the same as 1 over the root of 35. So theta is going to be equal to the inverse cosine of 1 divided by the square root of 35. And 80.3? About 80.3 degrees. And you know, comparing that with the diagram, I mean, it's tricky business, obviously, because it's dependent on your ability to come up with a diagram that looks reasonably like the coordinates are suggesting. Yeah, it's like I to j. All right, it kind of looks acute. J, I'm sorry, V, I said I to j, sorry. V to I looks acute. V to j looks obtuse. V to k looks acute again, right? Maybe pretty close to a 90-degree angle. But again, this is floating in space, so just because it looks like it's on the y-axis doesn't mean that it actually is. It's just a perspective drawing, right? So the best we can do with our two-dimensional brains. So that is a done page. Movie reference? Yeah. Very good.
What was it?
Return of the Jedi.
Oh.
Start with Star Wars and work your way out from there. And you can always
Which episode? The first one before
Return of the Jedi. ROTJ. All right, so on the next page, we have some examples that talk about finding the projection of V onto U. If we multiply the projection by a unit vector, we can get a brand new formula, but that formula is really just the projection multiplied by a unit vector. So you have to be specifically asked to find a unit vector that represents the projection of V onto U. All right, so it's a very specific type of question, but you'll see that going forward. All right, so anyway, these problems, it's really just relying on a formula. If you need to find the actual vector itself, then you would multiply it by a unit vector. So let me take you through one and then we'll call it a night. So I made it a trick question on a test one year, and I can't remember if I changed it from being a trick question. So be prepared for the possibility that a question on the test could say find the projection of U onto V. All right, so same setup, except it would be the magnitude of V on the bottom. All right, so. And I would totally consider changing it, except I think I'll totally forget to change it. So, u dot v, so we're looking at -3 plus 20 plus 3. That's something. It's a nice 20. Take it. All right. The magnitude of u, all right, so that's the square root of 1 squared, which is 1, 4 squared is 16, and then 3 squared is 9. All right, so we have 20 over the root of 26. I wanted it to be 25, but alas, that is not the case. All right, so what they're asking us for here is the projection of v onto u. All right, so we were able to come up with the magnitude of the projection, but I actually want the projection itself. All right, so what I need to do is figure out what that would be if it were multiplied by a unit vector in the direction of u. All right, because we are going on to specifically u. All right, so if you look at the formula, I mean, I went through the full-blown derivation here. For some reason, I opted to type this one out, but none of the other ones, I don't know what's wrong with me sometimes. But this first part here, the magnitude of v multiplied by u dot v over the two magnitudes multiplied, that's the magnitude of the projection. That's just a continuation. The other part is just the unit vector u. All right? So all I'm going to do is multiply this by u over the magnitude of u. All right, because I talked about this when we talked about unit vectors. What a unit vector does is it defines your system, just like units define a scale on an XY axis. You go by ones, you go by tens, whatever. Whatever you go by defines your scale. Right? Your unit vector defines really essentially one of whatever the vector is, one unit of your vector. All right, so if I know that this is amounting to 1 unit of that vector, then I multiply it by my desired magnitude, then I have the overall vector vector including the desired magnitude. All right, so this would be, I need a marker, equal, we have 2 over root 26. We have the magnitude of u, we already figured that out. So I'm going to multiply it by u divided by each part of u divided by that magnitude, right? Because the bottom of my component formula was the magnitude of u. So I'm going to take each one of these bad boys and divide by the square root of 26. All right? You could. All right, so clean it up. Negative 20 over 26. Simplify it in a second. Or simplify on the fly if you want. 80 over 26. 60 over 26. And so the projection of v onto u, so the amount of v that impacts u, so in the direction of u, was 20 over root 26. That was the magnitude of that. But if I were to go out in terms of a vector in the direction of u, this is how far I would get. All right, so negative 10 over 13, 40 over 13, 30 over 13. Decimal form might be more relatable just to get a sense of the scale. But we're talking less than 1, a little bit more than 3, a little bit less than 3, or between 2 and 3. So it gives you a little bit more sense of scale.
Is it all right to leave it as like 20 over 26 times negative 1, comma 4, comma 3, like with a scalar removed?
Yeah, it depends on the instructions.
Okay.
Yeah, just be careful of that. But generally, once you got to really this point here, you've essentially demonstrated the skill. So at that point, you're probably okay. All right, so star for the next question, and then we'll pick up with the cross product next class, and then that's it. So you want to be taking time. You know, I star all these problems, they're all well and good, but the best preparation for a test is the review problem set. There's a bunch of problems there. It goes through the entire unit. It's as you know, I mean, you don't need me to tell you, it's a lengthy unit. They're all lengthy units. So work through that before next class so that at the end of class, if you have questions, you can ask. All right. From last class. Okay, so we're projecting V onto U. Right, so it's the same process as what we did for number 11. It's just the vectors are written in a slightly different form. All right, so this is a vector that's in 2 space, or a pair of vectors that are in 2 dimensions. So I'm looking to find the magnitude of the projection of V onto U. And that's going to be U. I'm not going to rewrite the formula. It's U and V dotted over the magnitude of U. Right? So I need the dot product of the two. I mean, you may look at this as, I mean, the IJ notation, you might like that better. Personally, I like the bracket notation better. That's the way I like to do it. I find that generally, you as students probably like it the way you learned it first. And then think every other way is stupid. Well, why do we got to do it that way? The other way is so much easier. You're only saying that because you learned it the other way first. How do you know it's the same level of difficulty either way? All right, so yeah, it's something stupid like, I think it was 7th grade. One of my teachers said, "Bless you." No, she didn't say that. She said, "Perfect trinomial square." And then a year later, I had a different teacher who said perfect square trinomial. And it just sounded stupid in my mind. I'm like, you're saying it wrong. Meanwhile, the first teacher was the one that said it wrong, because it's supposed to be a perfect square trinomial. Like, the trinomial is a perfect square. All right? If you say perfect trinomial square, it's fine, it gets the job done, but it's not as correct as perfect square trinomial. All right? But my gut reaction was to be like alarmed by this. Like, why are you doing this? Why are you changing? You know, and so you take this class, you learn these triangular brackets, and then you go sit in a linear algebra class, and you get the square brackets, and you write the vectors on one on top of the other, 3 over a -2 with square brackets around, and you're like, what are you doing to us? Why can't you use the triangular brackets like the other class? It's just how it is, you know, human nature, I guess. Yeah, that's just the way it is. So. But when you look at it, what are we going to do? Either way, if I'm going to find the dot product between U and V, I'm either going to take the 3 and the 1 in this form and multiply them, or I'm going to take the 3 and the 1 in this form and multiply them. You don't have to do it one way as opposed to the other, as long as you get the job done. So 3 plus, oh, I don't know why that's purple. 3 plus -12. Figure out what that is in a sec. 1 plus 36. I mean, it's not much figuring to go on here. So it's over the magnitude of U. All right, so the square root of 1 squared plus 6 squared. So we're looking at -9 over the square root of 37. All right, so that is the component. Whether you know what that's called or not is. In this case, you know, it's not a big deal. Yeah. It's your problem. Yeah, it's not that big of a deal, because if you have an understanding of what this is representing, I think this is more meaningful. I went over this terminology last class, where it's like the component of V onto U. So the component of V that's acting in the direction of U. All right, that's cool. But if what's happening is V is being projected, you know, there's some part of V that's being projected in the direction of U, then the magnitude of that, I think it tells the complete story. So why do we have to give it another name? I have no idea. Right? So that is a magnitude. What we need is an actual projection. Right? So the projection takes this and multiplies it by a unit vector in the direction of U, right? Specifically in the direction of U. So I need U over the magnitude of U. Unfortunately, we already figured out the magnitude of U. So that's going to be 1 over the square root of 37 and 6 over the square root of 37. All right, so it's a unit vector in the direction of U. All right, so multiply the two things together and you have the projection. And so we're going purple here. Is that me? Jeez. And, you know, just depending on how a question's phrased, you may have to multiply it out. So negative 9 over 37, negative 54 over 37. I'm not big on asking people to simplify on tests too much, usually once, maybe twice, depending on the test. Every other time, you would want to leave it in unsimplified form, right? So that would, in this case, mean the step prior to the final answer. Right? So, you know, it's not much of a break that I'm cutting you here, but it's something. You know, every little bit helps. Number 13 it's a fun problem, but I didn't star it, obviously, because there's no star there. Also, it's not a question I'm going to ask you on the test, so we're going to skip that for now. But basically, it's just a word problem that asks you to find the projection of W onto V, right? Because I think W onto V. Generation speed along that path. The current, yeah. Oh, this is like killing me here. Hold on. Kind of. All right, the cross product. We're going to learn how to use the cross product and its purpose. One thing we're not going to do is derive it today, though. All right, so that's good news and bad news. It's bad news in that you're not going to really truly get a sense of how this formula comes into being, but we are going to be able to work with the formula. So the bad news is basically what I just said. You know, so you're going to work with a formula, and it's like, where did this formula come from? It just exists. Right? We will go over it. It's just not. It's not something for tonight. The good news is that I'm not going to ask you to do it on a test if I'm not going to go over it in class. All right, so the part where you derive it. I am going to ask you to do things involving the cross product. It's just not going to be the part where you actually prove the formula works the way it works. I will give you a little bit of a setup on it if it's something that you want to play around with. It's telling us, given two non-zero vectors, there is a vector that is orthogonal to both of those. So what would that look like? You would have two vectors floating around in space. Well, not really floating around. They're pinned at the origin. But then emerging from their intersection would be a third vector that's orthogonal to both of them. All right. So these two vectors are living on a plane. That's my attempt at drawing a plane. This vector is perpendicular to that plane. Now the possibility is that it could go also in the opposite direction. All right. So you could have a vector coming outward or downward, right, in the way this is drawn. All right. So how would you know? Well, it all depends on which one you're starting the cross product with. All right. So if this is vector u and this is vector v, then this one here would be u cross v. All right. So how do I know that? The way I learned it was using the right-hand rule. Right, so, oh, sorry. I used the right-hand rule in my mind, just I used my left hand, so it's kind of a problem. It's v cross u. I'll demonstrate it in a second.
I mean, wouldn't you just find the vector that's orthogonal to either one of them and just say that's it? And even if you get the wrong side, I mean, they're both, like, whichever one you get, they're both perpendicular. So if you get the one side of the other side, it doesn't matter.
Well, just because you're orthogonal to one of them doesn't mean you're going to be orthogonal to the other. That's the issue, because if you got two of them floating in space, I could have one. So in theory, what I would want is this vector, right? But I could get that vector, because this one would be perpendicular to one of the vectors, but not both of them, right? So the cross product would get you something, it'll get you a third vector that's perpendicular or orthogonal to both of the original vectors. All right, so the right-hand rule is just telling you to take your hand, and the part of your hand that includes your pinky finger. I don't know, how do I overcomplicate this anymore? And place it on one of the two vectors. If, when you're closing your fist, you're moving your fingers towards the other vector, then you have the result of the first vector cross the other one, right? So here I'm starting off at V and I'm closing in towards U. My thumb is pointing where that resultant vector would go. So this would be the result of V cross U, and the resulting vector V cross U would be coming out of the paper. This is my attempt at drawing a vector coming out of the paper, right? If I were to try to go from U to V, only using the right hand, no, I mean.
Yeah, you go inside the board.
It's like, okay, you know, I'd have to go the other side, right? So if that's the case, then I'd just be pointing in the opposite direction, all right? What I do generally is just place my right hand in a way that allows me to figure out a resulting vector and then just go off of that. So if I'm looking for U cross V, well, it ain't this one, right? Because this one is V cross U. So if I'm looking for U cross V, it would have to be the other one, right? So you just kind of figure out whatever you can figure out based on physical constraints. I mean, you have a hand and you have a piece of paper. There's only so many ways that you can use your hand to place it on that piece of paper. Use that information to draw conclusions about other possibilities. Right? Well, we'll see it in action in a couple of minutes. But generally, I mean, if you're asked to cross U and V or cross V and W, it's an operation. There's really no need to, visualize it, but to have a sense of the relationships, kind of, it's a good thing. All right. So if you were to derive this, what you would be doing is taking U and dotting it with V. So U1, U2, U3, dotted against V1, V2, V3, the result would be equal to that third vector, W1, W2, W3. All right, and what you'd have to do is solve this. All right, so like I said, a different story for a different day. All right, because I trimmed the amount of space needed for this just to cut down on paper. When we do this together, you're going to want a separate sheet of loose leaf paper because it takes up the whole page. Right? There's a lot of algebra involved. All right, but we're going to cut to the chase here and talk about the rule. And again, I just said, note, use the right-hand rule to get a sense of the direction of the resultant vector. If I didn't go through my little spiel here, you'd look at that and say, I don't know what the hell you're talking about, dude. So cross product is this formula. Look at that. Good looking formula. U2V3 minus U3V2I minus U1V3, blah, 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 blah. It's disgusting. All right. So there's a cleaner version of it that involves matrices. And if you use this particular form, the calculations are much, much easier. So you just have to remember, and when we go through the derivation, you'll understand why this is the way it is. They alternate in sign. So positive to negative to positive, right? So I, J, K, right? So, and that's assuming that we're going for 3 space. But let me take you through an example. Saying find P cross Q. So we'll use the matrix approach. You're essentially finding a determinant of the matrix, but in a slightly different way than you might in a linear algebra course. So I'm looking for P cross Q. I'm going to label the top row IJK, which is already the first like weird application of this. Because if you sat through a linear algebra course, you might know that each row or column in a matrix represents a vector. But I, J, and K are in and of themselves vectors. So how can you have a vector within a vector? There is an answer to that. Again, different story for a different day though. So -1, 2, 5, 4, 0, -3. All right, so the breakdown for this. Couple of 2x2 matrices, well, in determinant form. And then I'll show you how to evaluate those. Again, not something you need to really bother with the calculator. Calculator can find determinants for you, but in a 2x2 square matrix, very, very easy to do it by hand. Bless. So, to find the matrix associated with I, if you look at the general form, you see it's everything except for the ones. There's no U1 and there's no V1. So basically what we're doing is we're taking everything except for the I column. Right? So it kind of has a Kramer's rule kind of feel to it. Right? So I'm taking everything except for the I column to make up the matrix for I. So 2, 5, 0, -3. For the matrix associated with J, I'm taking every bit of information except for the column associated with J. Right? Because you see we have U1, U3, V1, V3, but there's no U2, V2. Right? So that middle column is out. I'm looking at -1, 5, 4, -3. And then for K, the same relationship. Ignore column K, -1, 2, 4, 0. All right, the result should be a new vector. All right, so we're not looking for a solid answer. The result's not going to be a scalar. We're not looking for like 20. You know, we're looking for something comma something comma something else, or we could just leave it in an IJK notation. All right. To find the determinant of a 2 by 2 square matrix, we're going to take the product of the elements along the main diagonal. That's going to be -6. And subtract from that the product of the elements along the other diagonal. So 0. All right, so starting with the upper left-hand corner, it's diagonal down minus diagonal up. All right, so diagonal down is -6, diagonal up is 0. -6 minus 0 is -6. So we have -6i. Diagonal down, it glitched. Minus diagonal up. So it's -1 times -3. All right, it got a little covered up there. I'll try to get it back in. So 3. Sorry?
That one is -16.
Let's see. So 3. And then diagonal up is 20. So minus J is what I'm looking for here. So -17, but then it's negative on the outside. So -17 becomes +17. J. And then for the last one, diagonal down minus diagonal up. So 0 minus, and then diagonal up is 8. So -8k. You could also put it in component form, so -6, 17, -8. Either way. All right, so some cofactor expansion. If you took linear algebra, you might remember that term. You might not remember that term. You might just look at this and say, oh, that looks weirdly familiar. I feel like I've done that before. Well, if you took linear algebra, you definitely did. All right, so this vector, assuming we did the math right, you know, hit or miss, guaranteed to be orthogonal to both of these two vectors. All right, so this is the cross product of P and Q, guaranteed again to be orthogonal to both P and Q.
So if there's a line that's orthogonal to both, if we did Q cross P, we would get that, but negative all those values. So
Right.
why does it matter, like when we do the math, why does it matter that you get the negative or the positive version of either?
Direction. Like just based on some physical constraints. I mean, if you're talking about gravitational pull and you want it to be orthogonal, you'd want it to be going in the downward direction as opposed to upward. So context based on some physical application, most likely. For the cross product that I drew, like if you're going to be perpendicular to two vectors, you can come out like out of the page or you can go into the page. Right? One of them would be a positive version of the other, or one of that's not even necessarily the case. One would just be a negation of the other. It's the opposite direction. All right. So these are the properties of the cross product. Some of them are obvious. All right, like the distributive property, the multiplying by a constant, cross product of the zero vector. All right. I mean, it sounds fancier probably than it is. It kind of looks like a zero property, you know, just basic zero property. You multiply something by 0, you get 0, right? But the weird one, I think, would be V cross V, the cross product of a vector with itself, all right? So the cross product of a vector of itself with itself will equal 0. Visually, you know, if you're thinking about a vector that's guaranteed to be perpendicular to two other vectors, Well, it seems like there's a contradiction in there if the two vectors are themselves the same. All right. So the one that's guaranteed to work would be the 0 vector. Scalar triple product or a triple scalar product. That's another one like a perfect square trinomial or perfect trinomial square. It's the same idea. You can say it any way you want as long as those 3 words are in there. All right. So that's a juicy one because it involves a cross product along with a dot product. All right. The dot product part of it is not terrible. It's just you're not overly thrilled about having to do it on the heels of doing a cross product. All right. So in the case of these examples, some of them are fairly basic, but some of them involve a little bit more work. So let's just tackle. We'll tackle the first one, I guess. We'll see where it goes. So one thing I'll take as a typo is I didn't explicitly state in number 3 anyway that it's in R3. Oh, actually, do I want it to be in R3? This is an opportunity for me to decide for future classes what I want. I mean, it could be R3, it could be R10. It would just imply that I'm not working with vector K. I'll make it R2. All right, but it should still be stated somewhere. All right, and the example after that should be in R3. All right, so 2 dimensions, 3 dimensions. All right. So I'm crossing 2i with 3j. Now, you can look at your properties and see what's going on here. For example, you might look at the multiplication by a constant property. Right? That's telling us that if I have something like cu crossed with v, that's the same as saying c multiplied by u cross v. Right? So that c would be a coefficient for the whole thing. Right? So in reality, I have 2 of those coefficients. What I'd be looking at here is 6 multiplied by I cross j. Cross another j, but we'll cross that. We'll cross that bridge in a minute. All right, so this property of multiplication by a constant is telling me that I can pull out, if it's a coefficient for either one of them, doesn't have to be for both of them, for either one of the vectors in the cross, it can become the coefficient of the entire thing. Since I have 2 of them here, I'm pulling out the 2 and I'm also pulling out the 3 to make the 6. All right, so what I'd be looking at here, do you want to do the cross product by hand? Do you want to actually do it out? I don't.
Can't we not do it in 2 space because we're defining both our axes?
Oh, it has to be. It has to be 3 space.
Because it's K.
Yeah, because it's a third vector that's orthogonal to the other 2. It would naturally have to be in a 3rd dimension. Good call. So anyway, yeah, because the answer that we were about to get would have actually caused some eyebrows to go up. So let me just do a quick sketch here. Very quick, poorly constructed sketch. So here's my x-axis, y, and here's my z-axis. All right. So I'm looking at I against j. So I'm going to call this I. And this one j. All right. I'm just making up arbitrary distances, just calling it a unit vector. All right. So the question would be, what is a vector that is perpendicular to vectors I and j? Well, they're both on axes. So by definition, it would have to be something along the other axis. Right? So really the question would be, is this gonna end up being something going upward or something going downward. All right, so we have two possibilities. Here's k, and here's negative k. I won't label the negative k. So I cross j, well, which one is that going to be?
Thumb down.
Thumb down?
No.
So negative k or thumb up?
Oh, I'm sorry, thumb up.
Thumb up, yeah. So I'd have to stand over here, but if I put my index finger along I and close towards j, my thumb points out of the paper. So that's in the positive direction. Right? So that would be a positive k.
So for J cross I, you would get negative K.
Correct. Correct. So I have 6k cross j, which would be the same as saying 6k cross j. So I just need k cross j. So if I were to try to place my hand on this piece of paper here, the best I can do with my right hand only would be to place it on j going to k. So that would bring me in the positive I direction. J to k would be positive I. So what's k to j? Negative I. So 6 times negative I. This is an option that you could use instead or in lieu of doing it all out. All right. And it only works because we're working with the standard unit vectors I, j, and k. All right? If we were working with anything else, you can't just assume the resulting vector would be something clean. You know, if I said you have a vector 1, 0, 5, and then vector whatever, this wouldn't work. It only works because we're working with the standard unit vectors. All right. So in the case of the example 4, we have I cross k. Right? You can look for a property, but if we're working off of this diagram, we would say, okay, well, let me try to place my hand in such a way that I'm going to get a vector out of this. I could do k cross I. So I put my hand here and close it towards I. That's gonna send me towards positive j. So I cross k would be what? Negative j. K to j, I think we just did that, right? Yeah, so that's negative I. So we're crossing two negatives. Well, you can look at this a different way too. Each of those vectors has a coefficient. You can look at this and say, I have negative 1j cross negative 1I. That would be the same as negative 1 times negative 1 j cross I. Which is just j cross I. And what would j cross I be?
K.
Negative K.
Negative k. Because I cross j earlier was a positive k. This would be the opposite of that, the anti-commutative property at work. So negative k. All right. So this is some mind-bending stuff, at least in the early goings. And some people are very resistant to this. And I think rightly so, because if your spatial reasoning isn't where you would like it to be, this could seem like gibberish. It's like, well, I don't see how you're going from one vector to another based on that diagram. It's just you have to sort of visualize that diagram in 3 space, right? So how do you begin to be able to do that? Geogebra is a really good resource. I mean, I don't get any money from them. So why do I push Geogebra on you? It's the best bit of software that I could find that allows people to become familiar with 3 dimensions. Right? So if that's the case, then what would be the harm in putting in your vectors and then putting in what you suppose the cross product to be, and there is a cross product feature. It'll compute the cross product and plot it for you, but put in what you suppose the cross product is, and get a visual sense of what's going on, because these two-dimensional diagrams, I'll tell you, this Calc 3, back when I was a student, all these the diagrams, they were kind of glossed over. It was like, just imagine this picture is what I'm telling you it is, and I do that a lot. But then my teacher couldn't say, all right, now if we go to the website and take a look at what the diagram actually ought to look like, it'll start to make a lot more sense. That, like, it didn't have that luxury, so it was like, oh, okay, I don't see how your diagram relates in any way, shape, or form to what you're talking about, but I'm going to go ahead and believe you, right? And you just kind of go that route, right? But then there were some diagrams where it just, it was like one of those perspective drawings, like MC Escher kind of things, where it's like, I don't see it. Oh, now I see it. I don't see it anymore. I had it. It was a nose, now it's a witch, the lady in a rocking chair, I don't know what's going on. Like, I had it for a sec, but now it's gone. Right? The blue dress, gold dress, that was like 10 years ago now. But that,
Is it really that long ago?
I think so.
Wow.
Yeah.
Wow, I'm old now.
Yeah, it was definitely a while ago. But that was one of those where it's like, yeah, it's blue. It's blue. Oh, no, it's gold.
Like Laurel
Look at it like
Yanni.
this.
What's that?
Like Laurel Yanni.
Yeah, that's that. So that's the idea. And in fact, let me take a minute here because I love GeoGebra.
Isn't there a lot of math involved into creating stuff like that?
Yes. There definitely is. So I'll just delete it. I want to go to these. Yeah, so definitely, I mean, again, it's free. It's never gonna cost money. I had a workshop on Friday at school when all the students were off and the teachers had to go in. Yeah.
Get a snow day.
We did not get a snow day.
Oops.
Yeah. So anyway, one of the workshops was related to GeoGebra. It was kind of funny because the guy gave us like a whole history lesson on GeoGebra, and then when it came time to us for him to tell us how to actually use it effectively, he's like, "Oh yeah, you're gonna have to find someone else for that. I don't really know how to use it. I just know why it's valuable." I'm like, "Why are you here? Like you brought nothing to the table here." So anyway, it was. I'll just do something simple, like I cross K. So let me get I in there, 1, 0, 0. And then create the vector going to that point. I'll bring it in a little bit so you can see it. Ooh, too much, overshot the Mac. All right, so that's our vector I. I can label it if I want, but it's not really important. And then I'll do K, so 0, 0, 1. Oop. So vector B. All right, so there's a function called cross, and it asks you for two vectors. That sounds precisely like what I want. Cross U and V. All right, and it gives us 0, -1, 0. It plots it for us, so you can see here that you're talking about a third vector that's orthogonal to the first two. All right, so you're getting the visual, the kind of visual that you would never get from my crappy drawings. All right, I turn off the axes and you can see it even more. All right, definitely a perpendicular relationship. Now, in terms of the actual measure there, well, that looks, 0, 1, 0 would be J. This is the opposite of that, so it would have to be -J. All right, so you get a good visual relationship, get a good sense of, how these things work in space from GeoGebra. I can't emphasize it enough. Some of the tech assignments, I always introduce the first tech assignment after the first test. There's a reason why, but I'll talk about that after the first test. But it's all related to GeoGebra in this course, right? And the reason is I'm going to kind of force you to explore what these graphs look like, because it does make a big difference, right? And I can't really emphasize it enough. I didn't really truly understand a lot of this material until I had the wherewithal to be able to investigate what the functions look like. You know, I was finding partial derivatives, and I was doing multiple integrals. It was all like, okay, just do this, do that, and get an answer, and it was all great. But once I actually saw what the surface looked like, and I was able to see it from different vantage points, it all made sense, right? So I'm hoping to be able to create the same thing for you. All right. And GeoGebra, it will never cost money. That's the one thing that I was able to take from that nonsensical workshop, is that what they're partnered with like Pearson, so that Pearson can use their images in their textbooks. So they're getting their money from the big companies so that they can offer free accounts for individuals. So students will always get it for free, students and teachers. The companies have to pay for it, right? So, I mean, how often can you hear, you don't hear that ever, right? The companies have to pay for it. We get it for free. It's usually the other way around. Some big executive going on a free vacation at the expense of us. So this is the opposite of that. So definitely take advantage of it. All right. Magnitude of the cross product, another formula that we'll invent down the line, but not today. It's a nice relationship, because you know, based on what we were talking about previously, that coming up with a cross product is kind of a pain. But the magnitude is not. Magnitude of the cross product, so basically, if I didn't have this formula, I'd have to figure out the cross product and then use the magnitude formula to determine what the magnitude is of that cross product. Here, as long as I know the magnitudes of the two individual vectors and the angle in between them, I'm good to go. So the issue becomes, how do you figure out the angle between them? Well, we know how to find the angle between two vectors. It's not always fun. But in this case, you're looking at something that's on the j-axis, or the y-axis, and something that's on the z-axis. So you could figure out the angle between them, but they're not always going to be that simple. So let's just do it out. All right. So magnitude of u is going to be equal to 4. Magnitude of v is going to be equal to 3. You don't need formulas for those because they're on the axes. All right, they're linear distances away from the origin. Just count boxes. All right, 0, 4, 0 is 4 units away from the origin. 0, 0, negative 3 is 3 units below the origin. All right, so 4 and 3, those are the operative terms. Then we're looking for the cosine. I know the formula says sine, but I need the angle. Cosine of theta is u dot v over the two magnitudes multiplied. All right, so great news. The dot product between u and v, I mean, you see a lot of zeros in there. There's a reason for that. That's because the dot product is going to be equal to 0. Well, a consequence of that is that the dot product is going to be equal to 0. All right, so therefore, theta is equal to 90 degrees. Looking for the angle separating two vectors, which way are you going to go? You're going to go the shorter way. All right, so as a result, I need the cross product. I need the v in there first. The magnitude of the cross product, which is the two magnitudes, so 4 times 3, times the sine of whatever the angle is that's separating the two. So the cross product, again, the vector that's orthogonal to the two given vectors, it's some third vector. I don't know what it is, but I do now have the ability to find the magnitude of that vector, in this case, 12. Sometimes a question, and you got to be prepared for this because I don't always telegraph what I'm looking for. Although, if you had an opportunity to look at that file I sent out earlier, I am telegraphing some information, like question 1 will be this kind of question, question 2 will be that kind of question. So You know, there's some things I say where you're like, well, you already told us which question is going to be the cross product question, so yeah. But yeah, when it says find a unit vector orthogonal to both A and B, the orthogonal to both A and B part of it is addressing the concept of a cross product. So I got to find the cross product. All right. Now it's a unit vector, so the answer is calling for a vector. That vector should be in unit form, so I'll have to find the magnitude of that vector. So I got to find the cross product, and then on top of that, I got to find the magnitude of the cross product. So this is a question of, you know, do I want to use this formula if I got to create the cross product anyway? Probably not. So let's go through the process again, because we only did it really the one time, so it never hurts to do it a second time. A cross B. All right, find a unit vector. So direction is not important. Could go either way. I'm looking at IJK. All right, this arrangement of elements within the matrix corresponds to A cross B. If you were to write, for example, B cross A and then still write the same matrix, you're incorrect, right? Because this corresponds specifically to A cross B. All right, so I'm looking at 2, -1, -1, 4, I. That's not an I. That's an I. Minus 5, -1, 0, 4, J, and then 5, 2, 0, -1, K. All right, so diagonal down minus diagonal up. So 8 minus, this would be a +1, so 7. On the down, it's 20. On the up, it's 0, so -20. J. On the down, it's -5. On the up, it's 0, so -5, K. All right, so that's the cross product, A cross B. They're asking specifically for a unit vector, though. So I need the magnitude of that. $474. All right, so we're looking at the unit vector is going to be 7 over the square root of 474, sorry, I minus 20 over the square root of 474, J minus 5 over the square root of 474, K. And I think they're all interesting, but you know, it's all in the eye of the beholder, I guess. So we have vector V, which would have a magnitude. And vector U would also have a magnitude. But you know, just going off of right triangle trig, if I were to say, for example, let's pretend that this vector v sine of theta wasn't there. You know, like just pretend it wasn't there. I would be looking at a triangle with a given angle theta, some known magnitude, and really nothing else. All right. So the question would be, all right, well, what would I do with that? All right, because you know the diagram gave us v times the sine of theta. You look at that and say, well, everything will make perfect sense if I knew what that piece of information was. But if I wasn't given that, I wouldn't know what to do. Well, let's just start with the idea that the area of a parallelogram is base times height, just like the area of a rectangle, right? So all the parallelogram is a slanted rectangle. If I were to take this triangle, cut it off at the dotted line, dashed line, pick it up, put it over here, I'd have an equivalent rectangle whose area would be determined by the length of the base multiplied by the height. All right? So the base itself would be the magnitude of whatever vector u is. The height would be the v sine theta, which is all well and good, but how do we get that? Well, I'm looking for a height, so I'd put a little h here, and then use SOHCAHTOA. I have an opposite side, and I have a hypotenuse. So the sine ratio, sine of theta, would be h over the magnitude of v, which corresponds to the height being equal to the magnitude of v times the sine of theta. So that's where this piece of information is coming from. All right, it's all Pythagorean, you know, SOHCAHTOA related, so right triangle stuff. All right, that's why I spent so much time in algebra and trig learning about right triangles, hardly spending any time on any other kind of triangle. You're like, oh man, we spent a lot of time on quadratics and right triangles. They're the foundation of everything else, so that's why. All right? So the height is now v sine theta. So v sine theta. That's the area of a parallelogram. It also happens to be the magnitude of the cross product between u and v. So it's really just a question of cross product. If I ask you to find the area of a parallelogram, I'm just asking you to find the cross product between any two adjacent sides, because that will give us the area, assuming you find the magnitude of it, it'll give us the area of the entire parallelogram. The only challenge is going to be figuring out, based on the coordinates that you're given, what two sides are adjacent to one another. So we figure that out by coming up with a quick sketch. Very quick. Very rough. So draw some axes. 1, 1, 0. So that's 1 in the x direction, 1 in the y direction. I'll label it up. And then nothing in the z direction, so we're on the xy plane. So here's 1, here's 1. Create a parallelogram out of that. Overshat the Mac. That's going to be point P. Point Q would be 7, 1, 0. So 7 units in the x direction. 2, 3, 4, 5, 6, 7. Still 1 unit in the y direction, but still on the plane. So that's Q. 9, 4, 2, and 3, 4, 2. Well, I don't know where those are going to be specifically, but I do know that I have to go out 9 units in the x direction, then 4 units in the y direction, and then upward. So I'm just gonna kind of ballpark it. I don't know exactly where it's gonna be. It's gonna be somewhere around, you know, like over here in space, right? Just based off of general movements. So 9 this way, 4 this way, and then up 2 units. So somewhere around here, right? Put it anywhere you want, because we're starting to get a sense of the shape of this thing, and that's really all that matters. So 3, 4, 2, we're talking about something that would generally be in this area over here. All right. Because again, all I care about are adjacent sides. Get a general sense of the placement of the coordinates, and then you can figure out adjacent sides. Adjacent sides give us adjacent vectors. All right, so here's one vector, P to Q. Here's another vector, P to S. If I find the cross product between those two vectors, I will have the area of the entire parallelogram. All right. So I'll need those vectors. So it's P to Q, so subtract corresponding components. Q minus P, so 7 minus 1, 1 minus 1, 0 minus 0. So 6, 0, 0. And then P to S. Corresponding parts, 3 minus 1, 4 minus 1, 2 minus 0. So 2, 3, 2. All right. There's a few possibilities. I mean, you could have done P to Q, P to S like we did. You could have done Q to P, and then Q to R. Maybe R to Q, R to S, S to P, S to R. But you can't do something like P to Q, P to R, right? Or even, you know, just getting the ordering mixed up. If you did Q to P and then S to P, they're not pinned down to the same location, so you need that commonality in the first point in each vector.
I'm sorry, how is P to S? Didn't you say it has to be like on the same plane or something, or was it?
No, not in the same plane. They just have to be adjacent sides in the parallelogram. So if I were to actually sketch out the entire thing, it would be, you'd have a parallelogram that looks something like this. P to Q and P to S would give you some adjacent sides, but you could have done Q to P, Q to R, S to P, S to R, R to Q. So as long as you're pinning consistently at the same coordinate for each vector.
Not P to Q and R to S.
Exactly. All right, so I need to find the magnitude of the cross product between these. Now, you may look at this and say, well, I like the shortcut formula, so let me find the angle between them. And that's entirely up to you. Question?
Yeah. How did you get the? Why did you do P to Q and we did the? You subtracted Q from P. It's like 7 minus 1 instead of 1 minus 7.
Oh, so you're always subtracting. Sorry, I'm just making.
It's like you're counting the steps.
Yeah.
That's how I try to do it.
That's essentially what it is. It's like movement from P to Q, if that makes sense. Mm-hmm. You know, because we're basically transforming this, so P goes to the 0 vector. So if I were moving P to 0, I would be reducing the x value by 1, reducing the y value by 1, and not changing the z value. So that subtraction, just doing Q minus P, accomplishes the same thing.
The size of the vector.
Right.
That's what you would say.
Essentially. So at this point, you're at kind of a crossroads. You would say, I'm either going to figure out what the cross product is and then determine the magnitude there, or if you think it's easy enough to come up with the angle, then you'd figure out the angle and then use the shortcut rule, right? In this case, because we have something that's on an axis, 6, 0, 0 is nice to work with. Maybe you go with the shortcut, which admittedly isn't always a shortcut. If that's the case, I'm going to find cosine of theta is equal to the dot product between the two vectors over the magnitudes of each of the two vectors. Dot product's easy because there's a lot of zeros in there. It's just 12. Then each of the magnitudes, well, the first one's 6. Then we have 4 plus 9 plus another 4, so root 17. All right, so that would give me, I'm going to leave it as a as an inverse cosine function. So cosine as an inverse of 2 over root 17. Instead of working with the decimal, I'm just going to leave it like that because I'll put that in as my angle in my magnitude for the cross product formula. So I'm looking at cross of PQ and PS, but specifically a magnitude. The benefit of this approach is that all the ingredients for this formula, we've already figured them out. So we know what the magnitude is of PQ, that's 6. The magnitude of PS is root 17. So 6 root 17 times the sine of the inverse cosine of 2 over root 17. Now, depending on how exact you have to be, you may opt to do a little right triangle stuff with this because we have an ratio, sorry. This is adjacent over hypotenuse, corresponding triangle. So 2 over root 17. If I want to find the corresponding ratio, I just use Pythagorean theorem to find the missing side. So 2 squared plus, let's say b squared, is equal to root 17 squared. So that's going to be 17 minus 4 is going to be 13, so root 13.
So when we have PS is really our V magnitude. So that's where we pull the sine theta from, and theta is the cosine negative 1. That.
Right, from over here. So we're looking at 6 root 17, and then the sine is opposite over hypotenuse. That's root 13 over root 17. So this would end up being 6 root 13. But that's only if you had a requirement that the answer is in exact form. I mean, possibility, so something to keep in mind. But also, I've showed you ways to get around this. You know, if you understand that whenever you do inverse sine, inverse cosine, whatever it is, depending on what type of function you're doing, you're performing the operation on in your calculator, it might be a multiple of pi. In which case you divide out the pi, see what you got. If it's something like the sine, cosine, or tangent, and you get a funky decimal, it's the square root of something, so square it and see what it is, and then simplify after the stuff. All right, so do you need to do this triangle stuff? Not necessarily, but it's a good skill to have in your repertoire, I suppose. The next one looks like it would be kind of unrelated, but it's actually very related. I'm not actually gonna go over it, but I'll just tell you what the key to success is in this problem, because it's saying you have P, Q, and R that represent the vertices of a triangle. All right. Well, we don't have a formula that helps us figure out the area of a triangle with vectors, but we do have one that involves the area of a parallelogram. So what we do is we create a parallelogram out of this. All right, so if I were to figure out, for example, I'll pin it at Q. At a vector QR and vector QP. If I were to find the magnitude of the cross product between those two vectors, it's a magnitude, so it's going to be positive. Doesn't matter which way we go, QP cross QR or the other way. That's going to be equal to the area of the parallelogram. All right, so that's going to give me the whole shebang, all of this stuff, everything. So what we would do is just take the answer and divide by 2. We doubled the amount of area in the diagram, so it would only make sense that once we do the calculations that we would just chop it in half. All right, so that's something that you can try on your own. The last thing is the triple scalar product.
Professor, I'm a bit confused. Is it QP and Q on different planes, or you just look at it from the point of Q?
From the vantage point of Q, so
Okay.
Q is getting moved to the origin.
Oh, okay.
The triple scalar product, or scalar triple product, depending on how you like to say things, is this. It's a dot product after a cross product. So you find a cross product between two vectors and then dot it with another vector, you have a triple scalar product. But fortunately, that corresponds with the determinant of a 3x3 matrix, which we can do in our calculators. Finding determinants by hand, they vary in difficulty. They get more challenging as you increase the dimensions of the matrix. 2x2 are very easy, as you saw. 3x3 gets a little harder. Anything 4 rows and up, and all of a sudden it's like, oh, half the test is me just working through this one matrix. It sucks, right? But fortunately, the calculator does all this for us. What we get here as a consequence when we're finding the triple scalar product is the volume of basically a parallelogram that is projected into 3 space, known as the fun word parallelepiped. And yeah, it's like just making stuff up now. But this process will help you figure out the volume of a parallelepiped, so a parallelogram projected into 3 space with the minimal amount of work. All right, so that's the last thing that we're covering, and that's really it. So let me take you through an example, and you'll see that really this, the volume section is really just number 9. It's just now we're adding the context to it of saying, by the way, what we just got is the volume of a parallelepiped. One of the technology assignments asks you to create a parallelepiped, just so you can get a feel for how those work, you know, what they look like. But for now, it's just the process. So what we do is we're finding the triple scalar product, which is a matrix containing each of the vectors as a row, so the row vectors. All right, so this is the equivalent form to this. right? By figuring out the determinant of this 3x3 matrix, we're figuring out the result of this calculation. So then the question becomes, well, how do I do that? Well, we know how to type stuff in a matrix, so let's do that. I'll walk you through the process again. So you're going to go to second. You're going to hit that x-1 key and go to edit. You're going to make a 3x3 matrix. Then you're going to go back into the menu. Not edit anymore. You're going to go to math and find the one that says determinant.
First one, DET, right?
Yep. All right, so in your home screen, it should say DET of matrix A. All right. So, matrix menu, go to edit, type in 3x3, type in the stuff. Right, that's the important ingredient there. You got to type in all the stuff that we have. So 1, 3, 5, 2, -1, 0, -3, 0, -1. All right, so before I had mentioned that finding things like the dot product and even the cross product, it's not always worth it to do it on your calculator. This one is absolutely worth it to do it on your calculator. All right, so quit out of here. Then second inverse, so back into the matrix, go to math, option 1, DET, determinant. All right, so I capitalized it in my notes, it's lowercase. You got to tell it what matrix you're finding the determinant of. So back into the matrix menu, looking for matrix A, and you get a -8. All right, so that would be the triple scalar product. That's all this question was asking us to figure out. If the question was asking us to find the volume of a parallelepiped with a corner having these vectors. All right, so let me just kind of, I'm going to steal these vectors and make kind of a side example related to it. I'm just going to draw out what these vectors would look like. So 1, 3, 5. So 1, 3, 5, it's going to be about right here, so that would be U. V would be 2, -1, 0, so that's going to be like right here. I'll draw the arrows in a sec. And W, -3, so I got to go back a little bit. 0, and then -1, so it's going to be about right here. So we're looking at one vector, another vector, and another. All right. These would serve as the corner, and because they're pinned at the same location, specifically the 0 vector, this would form the corner of a parallelepiped. Oh, parallelepiped. All right. The diagram for this is astonishing. So if you want to see a full-blown parallelepiped, you can start working on, I think is it the first tech assignment?
Yeah.
Did you do that in that
I did
one?
Tech A.
And you did a parallelepiped in
I
it?
don't remember. It would look like that.
Mm.
Is the parallelepiped need to be on the test tomorrow?
What are you talking?
This concept, yeah.
With the concept.
Yeah. So, I mean, you won't have to draw one, but if you want to get a sense of what they look like.
You did like 3 points.
And then you created
Oh yeah.
opposites.
Yeah.
Okay. So it's the second part of the first tech assignment if you want to take a look at it.
Second part of the first tech assignment.
Yeah.
It's really quick, but there's like 2 parts.
Right. It's not assigned yet, but it's something that if you wanted to look at it, you
I
could.
tried playing around with the tech assignment. It wouldn't let me use any of the options that were
So
displayed, the interactive options, I think.
what do
Might
you
just
to display it?
Yeah, to display.
Because like when I did the first tech assignment, it didn't work. So then I had to close Geogebra, reopen it, and then magically just started working.
Oh, okay.
So it can act stupid sometimes.
Yeah, it can. All right. Well, we'll talk about it at some other point, I guess. But what you could do is.
Now it worked with me.
Oh, it works? 'Cause I don't. I tried doing it.
And you got to make sure that you're in the 3D format.
Oh, that's cool.
Because if you're in the 2D format, it's not going to work.
Oh, yeah, no, obviously. But.
You can look at this.
I have a question.
Oh, yeah, folks, you can leave if you want. I was going to go over how to do the bonus if you're interested
Bonus
in that.
sounds very nice.
Yeah, so some of you don't need to stick around for this. That's perfectly fine because it's a Ken puzzle. If you had me in the past, you probably know how to do those. Although, if you had me in the past and you didn't know how to do those, maybe you do want to stick around. All right, but this is what a parallelepiped would look like. It's just basically a parallelogram in 3 space. It's just the corner would have 3 vectors. By finding the triple scalar product for those 3 vectors, you're finding the volume of the whole thing. All right, so that's really all it's coming down. So in that last problem that we did, the volume would be equal to just an 8. If that's what the question was asking. But let me take you through a Ken puzzle.